right. Can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey. We are here in Jenny Jump State Park in Hope, New Jersey, once again on our second to last night at the observatory for the season until we go online only for the winter. Because ain't no one want to drive up here and try and park in a snowdrift. Insurance is a little too expensive over the winter too, but so we'll see you online over the winter. With that, I want to welcome everyone who is not only here on site, but joining us online, because that is right, we do live stream these on both YouTube and Twitch. So if you're ever not here and go, man, I wish I was doing something cool and fun on a Saturday, feel free to hop on either of those sites and say hi in chat. I do monitor that throughout the presentation. I think we had a car come in, so I want to give any people that were just parking a chance to get down here. I do want to encourage everyone to check us out on our website, uacnj.org. It's where you're going to find a list of all our upcoming talks, as well as links to our past talks, because we do save them. So if you're ever like, man, I had such fun at this presentation, I wish I hadn't missed Chirag's presentation on space trash, don't worry, you can still see it. And if you have questions, ask those in the comments. I will contact him and get an answer. Because chances are I don't know the answer. That being said, you can also reach out to us on our social media. We have Facebook, Instagram, we have a Discord server, all great places to ask questions, or even just share your cool pictures of the moon or aurora or whatever you do. Also on our website, you have a list of all our member clubs, because we are a club made up of other clubs, and one of the easiest ways to get into astronomy is to join your local club, if not just for ease of access and proximity, but also because they're going to give you the tips and tricks for stargazing in your neighborhood that perhaps we don't have, because someone in New York City, and we do have clubs in New York City, might not benefit as much from someone like myself, who only knows the tips and tricks for best places to view in here in Warren County, New Jersey, which is much more rural and less light polluted. That being said, we're going to get into the safety briefing for those of you who are here. If you need to use the restroom, that is the porta potty in the back. It is big, it is blue, if you can see color at night. It is also illuminated by red for ease of finding. We also have a little museum area and gift shop, which I will be manning after the presentation, because still they will not allow me to break the laws of physics and be in two places at once. Much to my dismay, I would love to be in more than one place at a time. Get so much done. Each of the sheds you passed when you were parking actually has its own telescope. The ones with the roof rolled off are open and have a volunteer running that. Feel free when you go out there to ask them questions and see what they're viewing in their telescope. We also have a number of volunteers who brought their own personal rigs and have set up on the lawn. I believe they're doing astrophotography. Stop that. And see what they are taking pictures of. That being said, when we go to leave here, do use your headlights. We prefer not getting run over. Headlights will allow us to do that and avoid being Frogger. However, it is the state park. It is dark. We might need flashlights to walk around. Please keep the lights pointed towards the ground, and so we don't accidentally blind people by doing quick, cool rave tricks with the flashlights, because no one likes getting blinded by the latest, greatest 100,000 lumen monstrosity from Amazon. I did that the other week. I did not enjoy it. But you are not here to listen to me blather on. You're actually here for Dr. Chirag Skolar. Dr. Skolar is a computational plasma physicist working at New Jersey Institute of Technology. He got his bachelor's degree in mechanical engineering at Boston University and his PhD in aerospace engineering at Virginia Tech. He is interested in all things plasma physics and special focuses on plasma material interactions related to renewable energy nuclear fusion devices, which is different than fission. Uh, Plasma turbulence development in Earth ionosphere and improving remote sensing capabilities of non-Maxwellian plasmas, none of which I understood, but he will more than happy to explain that to you in a way that makes sense.
Thank you very much for the introduction. Uh, so I'm very happy to be invited here to give this really cool talk on an idea I've been thinking about for a little while now on ways that we can connect things that we see in our regular everyday lives to things that are happening on the grandest of scales in astrophysics. Uh, Today's a beautiful day for observing, and every time I look at the night sky, I always feel very humbled by what I see. Right, I'm a little ape on a little rock drifting through this vastness of space. There's all these huge things out there, so it feels very humbling when I look up. But during my PhD, as I was studying and reading up on some of the research that I was doing, I came across something that I found kind of very profoundly beautiful in a way that connects us to this grander scale. And what I'm hoping I can do for you today is capture some of that beauty, and maybe you can feel a little bit of what I feel too every time I look at the sky, and maybe every time I take a cup of coffee or something. Now, most of you, when you uh, grabbed your cup of coffee in this morning, I don't know if you were thinking about supernovae when you were doing that. Maybe you were because you knew you were coming to the stock. But generally, I don't think that we think about supernovae. So hopefully, maybe the next time you're taking a cup of coffee, you'll be thinking about some of this and be like, "Oh wow, this is pretty neat stuff." So the talk I have for you today is an unstable fluid universe: how your coffee is like a supernova. So before I want to really get into the meat of the science and the physics of this talk, I want to go and look at some artwork. I'm sure we've all seen this painting before. This is The Starry Night by Vincent van Gogh. This is a painting of some town in France, and over it is this beautiful starry night. You have the moon, you have Venus, you have some stars, and you have this beautiful turbulent flow with these vortices. And it's really a painting that has captivated humanity for over 100 years now. And it's some of the stuff that's featured in here that I want to connect with both the physics of what's going on and what we can see out in the universe. So I just want to give everyone a second to just take it in and just look at this painting and keep an eye on some of the features that are in this painting, because what's really cool is the stuff that the artist used for inspiration for this painting is real life stuff that happens on our planet that we can observe, that also happens broadly in the universe. So I'll give everyone a second to do that. So let's go back to the title of my talk now. Let's really get into it. An unstable fluid universe. There's two words there in particular that I really want everyone here to get a good understanding of. And the words are unstable and fluid. We have a general colloquial idea of what we mean by when we say those words, but what does it mean when a physicist or an engineer talks about something being unstable or something being a fluid? So the first one that I want to do is the word fluid. So what is a fluid? First, let's start about what are our states of matter. Everyone yell out what the three states of matter are. Yes, solid, liquid, and gas, exactly. Uh, and the question I have is, which of these states of matter are fluids? We've got our solids. These are standard things that we learned when we were kids, but solids are particles that are bound together in a state that are, they're vibrating, but they're kind of generally in the area that they are. An example is just a bunch of rocks. Then we have liquids. Liquids they take the shape of their container. They're not really bound together. They can go wherever they want, but they still have a lot of collisions. An example is a glass of water. Then we have gas. Gas will take its entire container. The particles are going about all over the place. Example here is some steam because you can see that on a picture, but another great example is the air that we're breathing around us. So if I could ask the audience, which of these states of matter do you think are fluids? Liquid, yeah. Uh, Liquid is a fluid. It's the quintessential fluid that we think of, right? If when we're sick, the doctor says, go drink your fluid. So you go home and you drink your Pedialyte or electrolytes or whatever you drink, right? Uh, but gases are also considered fluids because they behave in a very similar way to the way liquids do. So the answer typically is liquid and gas. But even so, there are a few instances where we can actually consider solids as a fluid. When we're looking at some geologic features sometimes on Earth on these large time scales and these large compressive forces, you can view some of the solid rock on the planet as a fluid. And even some nuclear fusion applications, you can view certain solids as fluids as long as you have sufficient compressive forces. But the general answer is liquid and gas. Now, I was introduced as a computational plasma physicist. So I work in the state of matter that is usually known as the fourth state of matter of a plasma. And really, it's more of an ionized gas. We take the gas that we had from the previous slide, and those were neutral particles, and through some method, whether it's a large electric field or high temperature, an electron is stripped from that gas, and now you have a gas of positively charged ions and negatively charged electrons. Sometimes you have negative ions in there too, but generally for the work that I do, and for most cases, it's positive ions and negative electrons, and those are all moving around. And we can consider a plasma a fluid as well. And these are just some examples of plasmas that I'm sure many of us have seen before. For those of you who may have been very lucky last year, there was an aurora. This is not from here, but there's an example of the aurora last year during the big solar storm. The aurora made its way down to New Jersey, so maybe some of you got lucky to see that one in person. Certainly, every time you see lightning, that's a bolt of lightning is plasma being ionized as the discharge goes from the cloud to the ground, or vice versa. We've got the sun and every sort of star. Those are just big balls of plasma that undergo all their nuclear fusion to give us the light that gives life to us. And on the bottom left here, I have a picture from the Stanford Plasma Physics Lab. There's many, many different ways that we can create plasmas in a laboratory environment to study them for all sorts of different things. And these are just a few examples of things that we can see that we all understand readily. But plasmas are very ubiquitous in all sorts of applications that we use that we might not realize. So all the chips that are in our phones and our computers are made with plasma etching, so it's very useful for manufacturing devices. Plasmas are very important in our near-Earth space environment because every time we want to communicate to a satellite, we have to go through a layer of plasma, so we need to understand how the electromagnetic radiation is doing that. Another example is in nuclear fusion technologies. Very often we need to understand how we can confine plasma to be able to get some sort of nuclear fusion energy out of it to get a renewable energy source. So plasmas are very useful and very ubiquitous, and not just in places here, but all around the universe. Plasma is the overwhelmingly most common state of matter for regular matter. We're not including dark matter. For regular matter, plasmas is the most common state of matter. So we've got liquid, gas, and plasmas can all be considered fluids. So what do I mean when I say they can all be considered a fluid? What I mean is that really a fluid is just a way of viewing the universe. It's a way of looking at a particular problem and modeling it in such a way that the mathematics turns out to give us a really good answer. And really what it is when we can stop looking at the individual particles moving around and we can look at them more collectively and say, I don't need to worry about every individual particle. I can look at statistically the bulk of the particles have this sort of density, this sort of velocity, this sort of temperature and energy, things like that. And if you can do that, they can use these fluid equations. These are the Euler equations. I'm not expecting people here to understand what these equations are, but I do want to go through a few key things that we can get out of these equations and what makes these equations so powerful in modeling the universe with so many different problems that we want to look at. So really, these equations are just a fundamental set of conservation laws. The top one is the conservation of mass. The middle is conservation of momentum. And the last one is the conservation of energy. These are all standard things that we've all learned about in our physics classes, that all of these properties are conserved. So when we look at, in the fluid sense, we're just saying the things that we're looking at are conserved quantities, and we want to make sure that they're conserved. And we can look at the different columns that I have here. This first column on the left, this little curly d over a curly dt, that's time derivative. That's just telling us how this quantity, mass, momentum, energy, is changing with time. And if this quantity is changing with time, then something else must be changing to make sure that there's conservation. So the something else part of it is also some of these quantities might change with space. That's what this second set of terms is here with this upside down triangle with the dot. That's how we define what's going on with a change over space. And then because we have all these particles moving around, they're all undergoing collisions internally, and that manifests itself in a large scale thing as pressure. So this third set of terms is the pressure terms that show up in the momentum and the energy. And then the last set of terms is what generalizes this to whatever problem we care about. This is the Euler equation. They're like some of the simplest equations, but then you add on things depending on the problem that you care about. So maybe for air, these equations might work great. But if you wanted to model honey, for example, honey is a very different fluid. It's very viscous, and you need to take that into account. You're not going to model it correctly, so maybe you need to add viscosity, which gives you the very famous Navier-Stokes equations. For the work that I do with plasmas, maybe we need to include electromagnetism because we have charged particles that are going to be affected by electric and magnetic fields. Because we're doing a lot of stuff with astrophysical things here, gravity becomes a very important aspect of understanding these fluids. And there's chemical reactions, radiation. This list can go on and on. There's so many different things that you could add to it. But the basic idea is we've got this conservation law looking at changes in time, changes in space, and how these changes are affected by these additional terms. You can have multiple species of particles, so you could have this set of equations. So if you wanted to model the air around us, and we, for some reason, if we cared about the fact that most of the air is nitrogen, some of it is the oxygen we breathe in, some of it is the carbon dioxide we breathe out, and there's some other trace particles in there as well. If you cared about all that, you have a set of equations for each species, and you'd solve all of those together. For plasmas, you've got usually positive ions and negative electrons, so you might need to have two sets of equations for that. And depending on the source terms that you use and other equations that you might need, you can add additional equations to close your system. For example, you can have Maxwell's equations for a plasma, where if you have your charged particles affecting your electric-magnetic fields and your electric-magnetic fields affecting your charged particles, to solve everything self-consistently. So this is a really, really fantastic tool, and this works a lot of the times, but it doesn't work all the time. And the main reason that this works is that the main criteria that we have for when this works is if you have sufficient collisionality of your particles so that we can say that there's a large enough statistics for us to really make this approximation. Because if there's not, then you have to really look at what each individual particle is doing. That becomes a lot more complicated and more difficult computationally. So one of the ways that we can describe this collision properties, collision criterion, is looking at a value called the mean free path. We can think of the mean free path as it's defined as the average distance that a particle travels before it collides with another particle. So I have this particle over here. This particle started up on the top left. It undergoes a bunch of collisions and it ends up over here. And after each one of those collisions, if you take the distance that that particle traveled, you took the average of that, that gives you your mean free path. So we could think about this from the perspective of if we're, whatever problem we're looking at, if it's on the scale of that mean free path or smaller, then we can't really consider it a fluid because there's not enough collisions to give us the statistics to allow us to model this as a fluid. But if we're looking at a problem much larger than this mean free path, then we can do this sort of calculation. On the bottom, I have an equation for the mean free path. It's kind of a simplified version, but this generally gets the job done. So lambda is the variable for mean free path and is equal to 1 over n sigma square root 2. N is the number density of your medium. So you could think of that as the number of particles in a volume. So we could think of how this might affect your mean free path as, imagine you have two balls in a room. If I throw these balls in random directions, what's the chance that they're going to hit each other? Not very high. Now imagine I have 1,000 balls in a room. The chance that one of these balls is going to hit another ball is gotten much larger, so we could think about this as the distance that one ball travels on average before it collides with another ball is now shorter, making it more collisional. So that that means you can look at problem spaces that are a bit smaller because you have more particles, more collisionality. The other term, sigma, is the collision cross section. You could think of that as kind of the size of the ball. So if I had 1,000 small balls in a room going randomly, yeah, they might collide with each other, but we can imagine that it's going to take them longer on average for them to collide with another particle rather than if it was a room where I threw 1,000 large balls, right? So that's what this sigma term is saying. And now I've got this huge table on the right here that I want to go through to just give you a crazy understanding of how disparate all of these scales are, but how these equations that I showed in the previous slide can be used to model all these different things have been modeled using the fluid equations. We just have to make sure we're in the right regime, of course, but they've been modeled using the fluid equations. So let's start with the quintessential fluid, water. Water has a mean free path of 2.5 times 10 to the negative 10, and that is a value that is actually slightly smaller than the size of a water molecule. What that means is that a water molecule will move less than its own size before it collides with another water molecule, because this is in a state of matter of being a liquid, so they're very highly collisional. So liquids are very easy to model as fluids. Now let's look at air at standard temperature pressures, which is at 0 degrees Celsius, 100 kilopascals. Gives us something on the order of 10 to the negative 8. That's about the size of a bacteriophage virus. So if for whatever reason the thing you're trying to measure to model is about the size of a virus or a little bit larger, you're not really going to be able to use the fluid approximation for air. But as long as you're sufficiently larger than that, then you can. So that's the basic idea. If we're on the order of the stuff in this middle column, then you can't use the fluid approximation for the thing that we want to measure on the left. But if you're much larger than it, then you're fine. So let's keep going up higher in altitude. So the air on the peak of the mountain Sagarmatha, which in the west is called Mount Everest, that's 8.8 kilometers high. And we know that there's lower density over there because any mountaineer that wants to climb the mountain has to bring these oxygen masks, and there's all sorts of stuff here. It's called the death zone. That only gives you an extra order of magnitude in the mean free path. So it gives you go from 10 to the negative 8 meters to 10 to the negative 7 meters. That's about the diameter of the SARS-CoV-2, the COVID-19 virus. If we keep going higher to low Earth orbit, now we are 300 kilometers above the surface of the Earth. This is where I do a lot of research for my work in understanding the near-Earth space environment. The mean free path is 2.4 times 10 to the 3, so 2.4 kilometers. That is the size of Central Park. That means a particle travels the distance of Central Park on average before it collides with another particle. Now let's change speeds a little bit. Let's go to the center of the sun. Center of the sun is very dense, right? All the gravitational pull of the sun is pushing things to the center. It's very hot. There's all these nuclear fusion reactions going on. Center of the sun is on the order of 10 to the negative 14 meters, which is the size of a uranium nucleus. It's very, very, very small. If we go to the surface of the sun, or the photosphere, we get to 10 to the negative 5 meters, gets you to a white blood cell. Let's keep going higher. Let's go outside of the sun. Let's go into our solar system, the interplanetary medium. This is the stuff that exists between the planets. This is a mean free path of about 10 to the 10. That is half the distance from us to the sun. So we're getting to very large scales now. Let's keep going higher. Let's go to the interstellar medium. This is the stuff that exists in between stars, right? As we keep going further and further away, there's less amount of stuff, but there is still stuff there. Then we can consider it a fluid, even though there's so few things. This is gives us a mean free path on the order of 10 times the distance from Voyager 1 to the Earth, or about 10 times the size of the solar system, which is very large. And we can go even further. Now we can go into the intergalactic medium. This is the space of stuff in between galaxies. The density is very low, but the mean free path here is the size of the Orion Nebula, which is crazy to think about, right? A particle will travel the entire distance of the Orion Nebula before it is likely to undergo a collision in the intergalactic medium. And yet, for all of these cases, we can use the same equations that I mentioned earlier to model all sorts of different things, which I find is just really profoundly beautiful and cool, that we can just use a similar sort of mathematics to back out all of these sorts of interesting things. So I went at length about what a fluid is. Now let's talk about what I mean by the word unstable. My favorite way to explain instabilities is by considering a pendulum because it's something that we're all very familiar with, especially when we were kids we loved playing on the swing. So let's consider a simple pendulum. I think we all know what's going to happen. I've got a pendulum that I have here and I'm going to let it go. It's going to go. It's going to go down. After a little bit it's going to settle at the bottom, right? That bottom area that it's in is an equilibrium because there's no other force acting on it, so it's just going to stay there. But that's not the only equilibrium that a pendulum has. A pendulum has two equilibria. One bottom one, and that's the stable equilibrium that we just saw before. And then this top one up here, that's our unstable equilibrium. If we have this perfectly positioned upwards, this is never going to move. But what do I mean by it being unstable? What I mean is if I give it a tiniest kick, right? So what I'm going to do is I'm going to start a video here, and I'm going to start it now. Now it might take a bit, but what I've done here with this initial condition, it looks like it's straight up, but this is actually, I kicked it by 10 to the negative 13 degrees, ever so slightly, and it's technically moving, but there we go. Now, and there it goes. So all we needed was a tiny, tiny, tiny little kick, and it was so small, but it was enough to kick off this instability for it to move from its unstable equilibrium to its stable equilibrium. And that's what we mean by something being unstable, is that you have this tiny little push, and then it causes whatever phenomenon you're looking at to grow and grow into something else, and usually ends up into some sort of stable equilibrium afterwards. So a similar concept exists in fluids, but it's a bit more complicated than this simple pendulum that I have here. Now, I'm only going to be talking about two particular fluid instabilities, the Kelvin-Helmholtz and the Rayleigh-Taylor instabilities. There is a whole host of many, many, many other instabilities that exist in fluids and plasmas, and they're either whether they exist naturally and we want to understand them because they're cool, or whether they are problems that we need to look at from an engineering perspective. But I chose these two because these are some very fundamental instabilities that show up everywhere in our everyday lives and in astrophysics. And I also chose these because they're just really pretty to look at, so it makes for a very good public outreach talk. So let's start with the Kelvin-Helmholtz instability. So the Kelvin-Helmholtz instability is driven by what we call velocity shear. So we have, imagine, a set of fluids where one fluid is moving on the bottom at some velocity to the right. The other fluid on the top is moving at a faster velocity to the right. This is an unstable mode. If we have a tiny perturbation over here, that perturbation is going to grow a little bit, and then so this the second column here, the second picture, is our linear regime of the Kelvin-Helmholtz growth. And then we get to the third and fourth picture, we get to the nonlinear regime. What's going to happen is the difference in velocities is going to induce a vortical motion in these on this interface. And it's going to keep going, and gives us this beautiful roll up. Now there are certain factors that will damp this, so it's every time you see a velocity shear, it's not guaranteed you're going to be Kelvin-Helmholtz unstable. You could have surface tension, collisions, viscosity, some other things depending on the specific media that you might be looking at and problems that you're looking at. But these are general things that are going to damp the Kelvin-Helmholtz instability. And this is an instability that is ubiquitously found in our lives. We've all seen this instability many, many, many times before. And based on this general, at least some of these top pictures over here, could anyone in the audience, and it's okay if no one can, but can anyone in the audience think of something that they have seen that is actually a Kelvin-Helmholtz instability? Ocean waves. Exactly. Ocean waves are the quintessential example of the Kelvin-Helmholtz instability. You have water moving at whatever speed it's moving at. The air on top of it is moving at a different speed, faster, and that's going to induce the wave to form. And then as you get closer and closer to the shore, then you get to that nonlinear wave breaking regime that gives you kind of that vortex that I showed in the previous slide. And other examples over here on the right, this is a set of Kelvin-Helmholtz instabilities occurring over Hartford, Connecticut. And These are really neat too, because one of the things that uh, about this instability that makes it look a little bit different depending on the regime we're in is if you have some of these damping terms that I mentioned in the previous slide, you don't get that nice spiral. That spiral kind of bleeds into itself a little bit, so you get kind of some of these billowing shapes. Uh, but it's still, a very beautiful thing if you're lucky to capture these sorts of instabilities happening in the clouds. I was actually, I hope you could see it from over there. Okay, so on the bottom left here, I was on a flight earlier this year, and I was on a window seat, and the window was closed the whole time. I happened to open the window and look outside. And I was like, "Whoa, it's a Kelvin Helmholtz instability." It was the coolest thing ever because I work with Kelvin Helmholtz instability, so I wasn't thinking that I was actually going to see one on the plane. So this is a picture I took on the plane. I don't know if people can see it, but there's a very subtle curve of the clouds over here of the Kelvin Helmholtz instabilities. So that was really, really, really neat. Uh, so you could be on the lookout for some of these instabilities next time you're on a plane. It's not guaranteed, right? I've flied a decent number of times. That's the only time I've ever seen one. Um, but it's still really, really cool to see. Now, the next slide, I'm going to show. Yeah, that's exactly it. Yeah, at one altitude on the bottom where the rest of the cloud is, the air is moving at one speed, and above the cloud, the air is moving at a different speed. Now, I'm not a meteorologist, so I can't tell you like exactly why that's the case over here, but that the general fluid mechanism is that. Yeah. So here we have, I'm going to show a simulation of a Kelvin Helmholtz instability. I'm going to start that now. What we're going to see initially is you're going to see some of these large scale waves begin to form. And that's the linear phase of the growth of the instability. Then you're going to see these small waves and these roll-ups begin to form, and that gives us into the nonlinear phase. And what's going to be really interesting is, maybe I should have zoomed in for the folks in the back, but there's going to be some instabilities that occur, like right over here, there's these additional kinks, and over here, there's these additional kinks coming up top. We could think of this, we could see these as secondary or tertiary instabilities, right? As this vortex is rolling up, there's still now you've created a velocity shear on that vortex. So now that vortex has become Kelvin Helmholtz unstable over there. So you could have instabilities on top of instabilities on top of instabilities, and then you can get into sort of like fractal sorts of mathematics problems. We get into what we call the turbulence cascade and understand how energy scales from larger scales to smaller scales. I'm not going to go into that detail today, but there's a whole host of interesting physics and mathematics that we could get out just from this problem right here, and it also helps that it's just a very beautiful sort of simulation to look at. Now, we've talked about the Kelvin-Helmholtz instability here on Earth, and I've shown this really cool simulation. I want us to really just look at kind of the fluid flow of what's going on here in this simulation, because I'm about to show you a video of Jupiter, and I'm hoping you're as amazed as I am that you can see things that look very similar to this just occurring on Jupiter. So here we have a set of images that the Voyager 1 took as it made its way towards Jupiter. It took one picture approximately every 11 hours, which is 1 day on Jupiter. Jupiter spins very fast. And we can see all these sorts of instabilities and roll-ups developing because Jupiter spins very fast. It's a gas giant. So gas giants tend to have different velocities at different latitudes because of the way that they spin. So we can see all these different instabilities developing, and it's just really beautiful to see, and it's really cool to see how the fluid equations that we had earlier, which is what gave us the simulation. I'm gonna play that again because it's just so cool. Are It looks very similar to the simulation that we just saw, right? So the fluid equations really do describe the phenomenon that we're seeing very nicely. Now this was a set of images that we turned into a video taken back in the 70s, right, when the Voyager 1 project was. We have some more things now that are even closer. This is a close-up of the Great Red Spot by the Juno spacecraft. This was a picture taken in 2018. And this is a beautiful still that we can see very fine detail, finer than what Voyager 1 was able to give us, of the instability development. We see these large vortices in the Great Red Spot and these other smaller but still large vortices. And we see all these secondary instabilities develop. We see these billowing type Kelvin-Helmholtz instabilities over here that are not quite fully formed into the regular Kelvin-Helmholtz instabilities that I've talked about earlier. There's all these secondary instabilities over here. And when you look at this and you compare it to Starry Night, and it's just like, wow, you can see the similarities just from there. So I find this to be just a fascinatingly beautiful picture. Um, Now, Jupiter is not the only planet that this occurs on. I mean, obviously it occurs on Earth because I showed it on Earth, but there's other planets that it occurs on. Now, I will tell you, this is probably some of the best images and footage that I have of a lot of this work here. So I don't want to say it's all downhill from here in terms of visual beauty. Um, but this is some of the coolest stuff that we have. But then if we go to Saturn, this is a picture from Cassini in 2004, the Cassini spacecraft. We can see that the Kelvin-Helmholtz ability exists in Saturn too, for much the same reason that it exists in Jupiter. It's a gas giant. There's different velocities at these different latitudes, and we get this sort of Kelvin-Helmholtz instability shear forming. So it exists on planets, and that's really cool. But what's also neat is that it exists around our sun too, and presumably then other stars. So in coronal mass ejections, or CMEs, they are large ejections of large quantities of plasma from the sun. So I have here on the bottom left is an image of the sun. Oh, you can't see my cursor. Okay. So I only want to put the cursor here to give a perspective. The size of the Earth is in fact about the size of this cursor, just to give us a scale about what I'm about to show. So what I'm going to show here is we can see there's this flare on this side. I hope everyone can see that. I'll play it again. Yeah. Okay. So it just goes to show how huge this ejection of plasma is from the sun. That's a coronal mass ejection. It was a large amount of plasma that made its way, and now it's hurtling into space. But let's think about this, right? We have this large amount of plasma that is now hurtling through space. So this plasma is moving at a fast velocity, moving through space, and space is not an empty void. There's stuff around it. So it's moving at a fast velocity. The regular medium around it is not really moving comparatively. So we have this large velocity shear, and maybe that gives us Kelvin-Helmholtz instability to form. So this over here, this work on the right by Hoffman and Thomson 2011 was actually the first observation of the Kelvin-Helmholtz instability in a coronal mass ejection. And they have these pictures way over here at different times to show some sort of instability development. Now, there's many more ways to show that it's a particular instability that develops beyond just looking at this visually, because visually I'm somewhat unconvinced. Maybe this spot down here kind of looks like a Kelvin-Helmholtz instability developing. But there's more other ways that we could do this from a more rigorous mathematical approach of looking at wavelengths and turbulence cascades and frequencies and growth rates that back out with the theory of what we should expect for KHI. But so this was the first observation. Then we recently had another observation by the Parker Solar Probe, which I think is one of the coolest spacecraft that we as humans have developed. It's the closest object that we've put to the sun and is the fastest human-made object ever. Excuse me, sorry. So that's really neat. So what it happened to observe is there's a lot of noise going on back here, but there's a few things. If we look at where these arrows are pointing, we can see an angled line of Kelvin-Helmholtz instabilities in a coronal mass ejection. And really, this one over here, I think we can see a few billowing patterns. And what I find really interesting about this one is that the KHI that it shows up here looks very similar to the KHI that we saw in those clouds over Hartford, Connecticut, which I find to be really, really neat. And this is just such a different scale. Each of those things might be like the size of Earth or something. I don't know. Like this is huge compared to little clouds that we see, but it's the same sort of physics. It's the same sort of thing that's causing this, which I find absolutely fascinating. So this is Kelvin-Helmholtz instabilities occurring near and around the sun. Let's go and scale this even further. Let's go to galactic scales. What we have here is a galaxy, the N1404 galaxy, as observed by the Chandra X-ray Observatory. And what I want to point out is that galaxies are also in motion. Stars are moving in the galaxy. The galaxy itself is moving somewhere with respect to its intergalactic medium. So this galaxy N1404 in this dashed box is moving in this upper top right direction uh, with respect to its intergalactic medium. So we have motion of one thing with respect to another thing. Maybe this is Kelvin-Helmholtz unstable. Oh, and one other thing I want to point out is just the sheer scale of this plot. Right, this is a whole galaxy. This is 20 kiloparsecs. That's like what I think 10 to the 10 to the 3 times 10 to the 20 meters is my calculation that I have here. So it's just a humongous scale. So, and we think that the Kelvin-Helmholtz really can manifest in multiple ways here. It's really hard to. Oh, we can see on this one over here. Okay. Now, galaxies are much harder to observe than planets and our sun because those are really close by. Galaxies are much further away, so we have to make a lot more inferences. So we're not going to see like the beautiful pictures here that we saw beforehand, but we can still get a few things out. So because of the way that we expect things to develop, maybe we see right over here, and I'll get out of the way in a second, right over here, there's some features that are beyond the leading edge that are expected to be Kelvin-Helmholtz instabilities because of the way they might roll up as they shed off the leading edge. That's one way we think that Kelvin-Helmholtz instability might manifest itself. This is the same galaxy that I showed in the previous slide. On the top right here is the NGC 4649 or M60. It's also an elliptic galaxy, and it shows these interesting wing structures. So this galaxy is also moving generally in the top right direction, and we see these winged structures on the top and bottom. And if we do a simulation of another galaxy that's very similar to that galaxy of NGC 4552 or M89, we see these similar sorts of Kelvin-Helmholtz instabilities develop, get this sort of winged structure on the tail end of the galaxy here. So maybe that gives us an indication that this might be some sort of Kelvin-Helmholtz instability that's occurring in this galaxy. And what's really crazy to think about is this is a Kelvin-Helmholtz, this is this vortex happening, but like this is a galaxy. There are entire stars do in this vortex sort of thing. So that's really neat to think about. So we went up to galaxies. Let's go higher. Let's look at galaxy clusters. Right, galaxy clusters are a collection of galaxies that are to some extent gravitationally bound together. This galaxy cluster is moving with respect to. Now, I'm not an astrophysicist, so I don't know if there's something like intercluster medium or if it's still called the intergalactic medium, but it's moving with respect to whatever's around it, right? So what I have here is A2142, and this is an ongoing merger of two smaller galaxy clusters. This is, in fact, I think one of the largest objects we know of in the universe. And the relative motion is inducing this little, you can see this little sort of bump and these little bumps over here. We think those might be Kelvin-Helmholtz instabilities. And this is a galaxy cluster now, so this is, looking at galaxies doing these sorts of motions. So this is just very humongous scales, how we can look at the same sorts of things that is causing the waves that we're just seeing while we're chilling on the beach, is the same thing causing these crazy large-scale waves in a galaxy cluster, which I find absolutely fascinating. Now I'm going to go to a different instability. I'm going to talk about the Rayleigh-Taylor instability. We're going to go back to understanding the instabilities real quick. So this is an interchange instability that occurs when you have a heavy fluid on top of a lighter fluid. So let's look at an example over here of a very common experiment we all did when we were kids. You had oil on top of water, on top of syrup, and they all stayed where they were because they were different densities, right? We could think of this as the bottom state of our pendulum. This is our stable equilibrium. Now what if we took this cup and flipped it upside down? Now we're in our unstable equilibrium. As soon as we put a little perturbation, everything's going to come crashing down. The syrup's going to want to go down, the water's going to want to go down, and the oil's going to want to go up. And that instability is called the Rayleigh-Taylor instability. It requires an acceleration, typically gravity for us here on Earth that are gravitationally bound, which is all of us. And over here is an example simulation of how the Rayleigh-Taylor instability is expected to grow. So this first part is kind of our linear phase. We have some perturbation just growing. And then the second part, you see this sort of hammerhead mushroom sort of shape develop, and it continues and continues. And now in this slide over here, we have this really interesting feature, and I think some of the folks in the audience might be able to tell me here. What do we have here? We have a heavy fluid being pushed down and a light fluid being pushed up. What do we think that might create? The KHI. That might create the Kelvin-Helmholtz instability. So we could have secondary Kelvin-Helmholtz instabilities over here, and even at the bottom over here for some of these, we've got the bottom is still Rayleigh-Taylor unstable because you still have the heavy fluid on top of the lighter fluid and it's still pushing down. So you get these smaller Rayleigh-Taylor instabilities. So we get the similar sort of fractal turbulent pattern. We can get instabilities on instabilities on instabilities. Um, so that's a really interesting thing for us to think about. Generally, we don't. These happen on such fast scales that we don't notice those as much, but it's really cool to see that in the simulations. And these are very important for some nuclear fusion applications, which is where my knowledge of the Rayleigh-Taylor instability tends to come from. Now, this is also something we've all seen before. Can anyone give me an example of where they think they might have seen a Rayleigh-Taylor instability before? And I can give you a hint. This is the part of my talk that is related to the title of my talk. Coffee, yes. So we have seen this in our coffee before. For those of us that like our coffee with cream, at least. If you like it black, then you might not have seen it. But if you like it with cream, the mixing that that happens when you put the cream in the coffee is the Rayleigh-Taylor instability. So here is some coffee. I'm going to play this video, and it's going to go kind of quickly, but note that there are a few features of like the fingers, there's these wisps, and there are these hammerhead instabilities that show up in the Rayleigh-Taylor instability. So now that happened kind of quickly. So let's look at this again, and let's look at it in slow motion. So in slow motion, it's a bit more clear of what's going on. And it's going to pause right here. And you can see, like, there's a few instabilities right here. And after the talk, if people want to come by and look a bit closer, everyone's welcome to. You can see a few instabilities right here that look pretty much exactly like the simulation that I showed in the previous slide. And you can see that these regions of like light and then dark and light and then dark, and those are the fingers of the Rayleigh-Taylor instability as they're mixing throughout the coffee, which is really neat to see. And okay, and that's just gonna keep going, and you can see more of the turbulent mixing of the coffee over there. So that's your Rayleigh-Taylor instability, but this is not the only place that we've seen Rayleigh-Taylor instabilities. We've seen them whenever there's some sort of large explosion. This is an example. This is a nuclear weapons test back when the United States did above-ground nuclear weapons testing in the 1950s. And this is your typical mushroom cloud that we've seen over any sort of nuclear weapon. The reason that this is a Rayleigh-Taylor instability. That's kind of upside down of the one that I showed in the simulation. But the reason that this is Rayleigh-Taylor unstable is when the explosion happens, it takes the air that was there, and that air becomes really hot. And we know hot air rises because it's less dense. So now you have this really hot air that's less dense, and the regular air that was there before now becomes more dense, so that becomes Rayleigh-Taylor unstable, and that gives us this mushroom cloud. This happens naturally on the planet as well in volcanic eruptions. This is a picture from the International Space Station of the Sarychev volcano in Russia erupting in 2009. We can see the same sort of mushroom cloud as we see in the explosion on the left, right? It's also Rayleigh-Taylor unstable for the same exact reasons. So let's look at this not only on Earth anymore, let's look at it on the sun. So the RTI occurs in solar prominences. And I think this is actually the same picture that I had before, still from that image with the coronal mass ejection. A solar prominence is just some part of plasma that is sticking out of the sun. So we've got this loop here, and then there's that smaller bit over here. Sometimes it turns into a coronal mass ejection. Sometimes it doesn't, and it just eventually makes its way back into the sun. But regardless, within these solar prominences, you end up having a heavier plasma over a lighter plasma, and you've still got the sun's gravity, so that becomes Rayleigh-Taylor unstable. So here I have what's going to be a video, and I want everyone to focus on the bottom over here and some of the bubbles that are going to be coming up, because those are all going to look very much like the Rayleigh-Taylor instabilities that I had been talking about. You can see these bubbles of Rayleigh Taylor instabilities coming up from the sun because you've got this lighter plasma underneath this heavier plasma. So this is definitely just very uh, beautiful to look at too. Okay, cool. So this is so these are Rayleigh Taylor instabilities happening on a star that's still in a good part of its life. Now let's look a little bit ahead. Maybe not the sun. I don't think the sun's going to do this, but other stars. Um, let's look in the future of a star. So stars are balanced. They reach their equilibrium and maintain their generally circular shape or spherical shape by balancing their inward pull of gravity by the outward pressure of their nuclear fusion reactions going on inside, with all the energy and heat that they create. Now, when stars start fusing iron together, that nuclear fusion reaction no longer gives it enough energy to maintain that equilibrium to counteract its own gravity, and it's going to implode in on itself. And after it implodes in on itself, it will explode into a supernova. And when that happens, uh, you end up with a large shock wave on the outside, but then on the inside of that shock wave, you have the heavier inner plasma is now being pushed out into the lighter outer plasma, which is very similar to the Rayleigh-Taylor instability wave, but like instead of gravity, it's the acceleration of this explosion that's pushing everything out. So on this image here, this left part of the image, is it's a false color image of a supernova where we can see here's the forward shock, and there are these little patterns over here that we think are all Rayleigh-Taylor instabilities uh, because of the exact mechanism that I was just talking about. So now let's fast forward about 1,000 years. So let's say the supernova took place. Maybe there were some Rayleigh-Taylor instabilities. Maybe there weren't. It's been 1,000 years, and maybe we see something that looks like the Crab Nebula. It's a very beautiful image. It was one of the more recent images of the Crab Nebula from the James Webb Space Telescope. So in the Crab Nebula 1,000 years ago, a star became a supernova. And as it condensed, it resulted in what's called a pulsar, which is a rotating, very dense neutron star. So this very dense neutron star, it's spinning very fast, and that's pushing particles out away from the neutron star. And as it's pushing these particles outwards into the leftovers of what existed after that supernova, it also results in a Rayleigh-Taylor instability. And we can see all these beautiful fine-scale structures that are all Rayleigh-Taylor instabilities caused by this sort of motion. Right? It's not going to be like as nice and simple as some of the simulations that I might have shown, just because this is much more of a chaotic real-life situation where there's all sorts of different factors, but we can see all of these amazing Rayleigh-Taylor instabilities forming. And if you look at it and we compare maybe the coffee video I showed earlier, I'm hoping that we can see the resemblance between what we have here and what we have in the coffee. So here's a side by side. So hopefully we can see some of the resemblance in the fluid behavior of the Rayleigh-Taylor instabilities of the same thing in our coffee cup and things in the Crab Nebula. So with that, I hope that I've imparted some amount of this profound beauty and amazing way that we can view the universe to you, and maybe the next time you look at a coffee cup or you're at the beach, you could think about how the same sorts of things that you're seeing in front of you are existing on the universe in such grand scales. Thank you for your time, and are there any questions?
All right. Thank you so much for a wonderful talk. Okay, so we are going to have a question and answer session. But before that, I think I saw a couple of you sneak in after the safety briefing, and unfortunately, or fortunately, no, fortunately, the safety briefing is unescapable unless you start running and screaming away now. Don't do that, actually. But if you guys need to use the bathroom, that is the porta potty, and back to my left, your right. It is illuminated by red for ease of finding. I do have a little museum and gift shop area. I'll be manning that after question and answer session because Still can't be in two places at once. Nothing has changed with that between start of presentation and now. We do have a number of scopes that you will be able to look through and have volunteers manning them. Do ask questions. When we go to leave, we are using our headlights because we don't like playing Frogger in the dark, and ain't no one need the medical bills of getting run over. That being said, it is dark. If we have flashlights to move around because of that, I do ask that we keep those pointed towards the ground so we don't accidentally blind people. Now, how question and answer session is going to work, for anyone here who has a question, you're going to raise your hand and wave it about like you just don't care, and keep your hand up because I'm kind of night blind since I've been staring at a computer screen monitoring online chat. And therefore I am the Jurassic Park T-Rex, where my vision is completely based on movement. Online people, you have it easy. You just get to type and I get to ask it for you. Right, so with that, was there any question to start us off? Oh good, we have a question. I thought I was going to only have crickets for a minute there.
Excellent presentation. The instabilities you described, are those sort of the base level instability, or are other instabilities in the universe at large, like more frequent or ubiquitous than the one you've shown us?
That's a good question. I don't know about like what instabilities are more ubiquitous because there's so many different varieties of them. But these are the ones that we can see very easily that make for a nice talk. There's other instabilities that exist that are all over the place, that we might not be able to see necessarily from where we are and seeing, looking at a star or whatever. So yeah, I can't really fully answer that question, other than that yeah. I think that's my answer to that question. Yeah.
The fun thing about space, astronomy, science in general, is that it is very vast. So you pick your niche, and you learn a lot about your niche. And then outside stuff, you know some of it, but you can't know everything. That is impossible to know everything. So I feel the pain.
Yeah.
Right, so I want to do an online question, which was... Actually, this was a fun statement when you were trying to ask what unstable and fluid means. Unstable, one of my exes, fluid, cats.
Yeah, cats are fluids.
Right, and we got another question here.
So you mentioned alternate energy. How does that factor in?
Oh, I actually have a slide on this that I didn't think I'd have time to get to. So, this is an example. I don't work in this particular aspect of nuclear fusion energy, but nuclear fusion energy is a way that we can achieve clean, renewable energy without needing greenhouse gas emissions or whatever. It relies on how we can fuse isotopes of hydrogen together to create a lot more energy than we use putting into it. And it's kind of like the holy grail of renewable energy, and been working on it for a very long time. And we've gotten closer, but it's still a very hard problem. There's a lot for us to deal with. So I work in a different aspect of nuclear fusion energy than what I've shown here, but this is kind of the most related one to the Rayleigh-Taylor instability, where we could think of this method of creating nuclear fusion, inertial confinement fusion, as making like a mini controlled supernova. You have this little tiny pellet that I think is like this big, and you have all these lasers. So this is the National Ignition Facility. There's all these lasers that are coming down into one little area over here, and they're all bombarding either bombarding a capsule that makes X-rays to go into this target, or bombards the target itself to hopefully implode the target spherically symmetrically, so that it can fuse a bunch of hydrogen in the middle to get some energy out of it. Now, the problem is this, like what I said with the supernova, during that implosion process, you end up with this Rayleigh-Taylor instability. Now, these are actually measured experiments that they did. for different sorts of situations. But we can see this sort of Rayleigh-Taylor instability form on this solid pellet. So this is actually one of the things I was saying, that you can measure, you can model a solid as a fluid, because here we see that the solid is Rayleigh-Taylor unstable under these regimes. And the issue that we need to deal with understanding the instabilities here is we don't actually want that, because we can see here this ruins our symmetry. We want to keep the energy confined as much as possible, and if you have this Rayleigh-Taylor instability, that energy that you want it to go towards the center to create the nuclear fusion, some of that energy is actually going in to create these Rayleigh-Taylor instabilities. So there's a lot of research that's being done on how to mitigate the Rayleigh-Taylor instability.
I was going to ask whether that was some sort of gearing or MRI or X-ray of a spine, but you answered that.
I never thought about that. Okay, yeah, it does look like it.
Yeah, out of the corner of my eye when I saw that. Why does he have a picture of a spine? But yeah, was there? I see another question out here. And people in the back, you don't have to be shy. I have legs. I can walk.
So when you were asking for examples of Rayleigh-Taylor instabilities, you mentioned the coffee and the cream.
Yep.
Why isn't something like if you were to drop oil in water, why isn't that considered a Rayleigh-Taylor instability? Is it because of the viscosity of the oil mixing with the water? And is there like a scientific name or example of something in space or the universe that would be like oil and water?
So it's not oil on water, because that is Rayleigh-Taylor stable. So if you have oil on water, so if you have this example image picture I have here, if you have your water and you put your oil in the water, some of that, as you drop it, some of the oil might go down, but it's eventually going to settle back up to the top, right? So that gives you a stable equilibrium. If you did it the other way around, if you had your vat of oil and you put water in it, and make sure it's cold, please don't create an explosion in your house and burn yourself down. So if it's
Thanksgiving fryer turkey
yes,
experience.
none of that. Cold oil, put some water in it, and you will see a Rayleigh-Taylor instability form, because it's the same sort of concept as cream in your coffee. But there's going to be a little bit of a difference, because that's not going to mix quite as easily, because they're not oil's non-polar and water's polar. So there's going to be interesting things. I don't know exactly what's going to happen there. But you're going to see a Rayleigh-Taylor instability with water on oil versus oil on water.
Right. Online chat, if you have any questions, I do ask that you get those in. And I like to say that now, because by the time we get 2 minutes into the future, they finally caught up to us, to me saying that, because that's how stream delay works. Was there another question out here? Bueller? I love how when I say that, everyone just freezes. Like, no movement. She can't see me. All right. So just to give them a couple extra seconds, once again, thank you for such a great talk. I want to have you back for more talks. Thank you, everyone who has joined us not only here, but also online. Like I said, if you do check us out online, do hit those like, follow, subscribe, the free actions. Let us know we're doing a good job, and that you want to see more. If you're extra generous, you could always do the non-free actions, which goes to help upkeep of our environment, improvements to everything, and allows us to keep doing free outreach programs like we have been, because that has all since we are a nonprofit, that has all been supported by you guys, and I want to give you guys the thanks you are due. Our online viewer, I'm sorry, I'm gonna butcher your name, Vitrin, says kind of like a lava lamp. He love a good lamp.
Yeah, in a sense, we could think there's controversy on whether it's Rayleigh-Taylor instability or I think the Rayleigh-Bernard convection, but it's a similar sort of idea. A lava lamp works by you have you're heating up this fluid on the bottom, so it rises and then it comes back down. So it's similar to the Rayleigh-Taylor instability, but I don't think it's quite exactly like that. But it's a very similar idea. And then if you look at a lava lamp, you might see things that look somewhat like this image over here, actually.
Right. So, like I said, check out our website, uacnj.org. You'll find all sorts of fun information like our next talks and links to everything. Also, follow us on our social media, Facebook, Instagram. We have a Discord server. All great places to ask questions and share your space, science, astronomy experience. Oh, those are a pair of shoes. Like I said, my vision's completely movement based, so I'm like, haha, I saw someone. With that, everyone, have a safe night, clear skies, and good seeing.